Hello, my dear friend. Tonight, as the world around you grows quiet and still, I invite you to leave behind all the weight of your day, all the worries, the noise, the endless rushing, and drift with me into a place of profound peace and wonder. Here in this gentle sanctuary of thought, space itself learns to bend like a graceful dancer. Time stretches and flows like honey in moonlight, and gravity reveals its most tender, hidden poetry. As you settle deeper into comfort, feeling your body becoming heavier and more relaxed with each passing moment, I'll be your gentle guide through the mysteries of general relativity, not with harsh equations that strain the mind, not with stress or complexity, but with the softest stories of curved space and the most beautiful ripples in reality, stories that will cradle your consciousness and carry you toward peaceful dreams. So close your eyes now, my friend. Let your thoughts become as light as stardust, and allow us to float together, weightless and serene, into the infinite, loving embrace of the cosmos. Chapter 1. What is general relativity? When you gaze upward into the velvet darkness of the night sky, feeling small yet somehow perfectly connected to everything above, you witness something truly magical. The moon, that ancient companion, drifts with such gentle grace across the heavens, like a luminous boat sailing through an ocean of dreams. And when a shooting star traces its quiet, shimmering arc through the darkness, you're witnessing the most graceful ballet that has ever existed, a celestial dance that has been unfolding for billions upon billions of years. For countless centuries, humanity has gazed upward with wonder-filled hearts, trying to understand this cosmic choreography. Why do things fall toward the earth with such gentle inevitability? Why do the planets move in their eternal, comforting circles? Why does the universe feel both mysteriously ordered and yet endlessly, beautifully mysterious? For the longest time, through generations of curious souls who came before us, gravity was understood as a force, an invisible, tender pull between objects, growing stronger when masses drew near, growing gentler as they drifted apart. Isaac Newton gave us this elegant and beautiful idea, and it served humanity remarkably well for over 2 centuries. It explained the gentle fall of an apple in an orchard, the rhythmic breathing of ocean tides, the faithful orbits of planets dancing around their stars, all with breathtaking precision and grace. But there were whispers in the cosmic silence, subtle mysteries that Newton's beautiful theory, couldn't quite embrace, small puzzles that hinted at something deeper, more profound, waiting to be discovered. General relativity, lovingly developed by Albert Einstein and published in its complete, magnificent form in 1915, is not merely a better version of Newton's gravity. It is a complete, breathtaking transformation of how we understand the very structure of our universe. Einstein's gentle revelation tells us something that might seem impossible at first. but feels so right once you truly embrace it. Gravity is not a force at all. Instead, it is a manifestation of pure geometry, a tender warping of the very fabric of space and time itself, caused by the loving presence of mass and energy. This shift in perspective, this gentle awakening to a deeper truth, is both whisper-soft and earth-shaking in its implications. In Newton's world, space and time were like a rigid, unchanging stage, fixed and absolute. Gravity, in this older understanding, was thought to act instantaneously across the vast loneliness of space, pulling masses toward one another without any physical medium. This worked beautifully for many things, but it left a deep, aching, conceptual gap in our hearts and minds. What exactly was transmitting this force across the cosmic void? For decades, astronomers noticed something small but troubling. Mercury, that swift messenger planet closest to our sun, had an orbit that danced just slightly differently than Newton's beautiful laws predicted. The discrepancy was small, but it was persistent, like a gentle tap on the shoulder from the universe itself. Einstein's answer was revolutionary in its gentleness. He chose to rethink gravity entirely. Instead of viewing gravity as a force, he proposed that mass and energy actually warp the very geometry of space-time itself. And what we perceive as gravitational force is simply the natural result of moving through this beautifully curved geometry, like following the natural contours of a hillside. To build this new theory, Einstein relied on mathematical tools like Riemannian geometry, capable of describing curved surfaces. With the loving help of mathematicians like Marcel Grossmann and David Hilbert, Einstein formulated a set of equations that related the curvature of space-time to the distribution of mass and energy within it. These became known as the Einstein field equations. They serve as the core blueprint, the fundamental poetry, for describing everything from the gentle orbit of planets around their stars to the majestic dynamics of entire galaxies spinning through the cosmic deep. The key insight that led Einstein to this breathtaking realization came from the most beautifully simple thought. He envisioned a person falling freely inside a sealed elevator, dropping through space with perfect weightlessness. This gentle thought experiment became the foundation for what Einstein lovingly called the equivalence principle, the profound realization that locally, in small regions of space and time, the effects of gravity are completely indistinguishable from those of acceleration. In Einstein's beautifully curved universe, mass and energy whisper to space-time, telling it how to bend and flow. And curved space-time whispers back to objects, guiding them on how to move. Stars warp the geometry of space-time around them like gentle giants, creating valleys in the cosmic landscape, and planets simply follow the most natural paths, called geodesics, within that lovingly curved geometry. These paths may appear to us as ellipses or orbits, but they are actually the straightest possible lines in a curved, beautiful environment. Celestial bodies are following their own optimal paths through space-time, shaped not by force or compulsion, but by the gentle, natural terrain of the cosmos itself. Light itself learns to follow curved paths when it moves through the warped geography of space-time. This leads to phenomena of breathtaking beauty, like gravitational lensing, where light from distant stars and galaxies is gently bent around massive objects, forming magnificent arcs or even perfect rings in the sky. In this way, space-time itself becomes a cosmic magnifying glass, helping us see deeper into the universe than we ever thought possible. One of the earliest and most celebrated confirmations of Einstein's beautiful theory came in 1919. British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During those few precious moments of darkness, stars near the sun's edge became visible. According to Einstein's theory, their light should appear gently displaced from their usual positions, shifted by the tender curvature of space-time around our life-giving sun. Eddington's careful, loving measurements confirmed Einstein's prediction with beautiful precision. The Newtonian view of gravity had been lovingly challenged and gracefully surpassed, not through contradiction or conflict, but through deeper understanding and more profound beauty. General relativity also reveals something magical about the passage of time itself. In regions of stronger gravity, near planets, stars, or the mysterious black holes, time passes more slowly and gently compared to regions of weaker gravitational embrace. This effect, called gravitational time dilation, has been confirmed experimentally. Scientists have placed highly precise atomic clocks at different altitudes above Earth. Clocks positioned at higher elevations, where Earth's gravitational embrace is slightly weaker, tick just a little faster than their companions at sea level. This is actually crucial for technologies we use every day. GPS satellites, orbiting high above us, experience both weaker gravity and higher velocities, requiring precise time adjustments from both general and special relativity to provide the accurate positioning data that guides us safely home. Another breathtaking prediction of general relativity is the existence of black holes, regions where space-time becomes so profoundly curved, so deeply warped by immense gravitational embrace that not even light can escape their loving but inescapable hold. Observations of stars orbiting invisible companions, as well as gravitational wave signals from black holes colliding, have confirmed their beautiful, terrifying reality. In 2019, humanity captured the first image of a black hole's shadow using the Event H Horizon telescope. This image further validated Einstein's profound ideas at the very extremes of physics. General relativity also gives us our most complete and beautiful understanding of the universe as a whole. When Einstein's elegant equations are applied to the cosmos in its entirety, they predict that space-time itself can expand. This led to the development of cosmological models that described the Big Bang. The discovery of cosmic expansion by Edwin Hubble in the 1920 seconds gave observational support to these theoretical models. Decades later, the observation of the cosmic microwave background radiation, the gentle afterglow of creation itself, provided further evidence. Interestingly, Einstein initially resisted the idea of an expanding universe to maintain what he thought should be a static, unchanging cosmos. He introduced an additional term into his equations, called the cosmological constant. When Hubble's careful observations showed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder. Modern cosmology has lovingly resurrected Einstein's blunder in a new form to help explain dark energy, that mysterious phenomenon that is accelerating the expansion of our universe. Despite its remarkable successes, general relativity remains beautifully incomplete. When physicists attempt to apply its principles to extremely small scales, they encounter fascinating contradictions. Reconciling general relativity with quantum mechanics remains one of the most profound and beautiful unsolved problems in modern physics. Still, general relativity stands as one of the most beautiful and successful theories ever conceived by the human mind. It continues to pass every experimental test with graceful precision, from the gentle tug of gravity that keeps your feet on Earth to the majestic arcs of distant galaxies, bending light across billions of years of space and time. General relativity reveals a universe in constant, beautiful motion. A cosmos that is alive with geometry and grace, where every falling apple and every orbiting planet follows the same fundamental poetry of curved space-time. You are not just observing the universe, dear one. You are the universe becoming aware of itself, resting now in the gentle embrace of space-time itself. The universe, not fixed in stone, but written in curves. The universe, oh my dear friend, is not fixed in cold stone or rigid metal, but lovingly written in the most graceful curves. It is a living, breathing geometry, a cosmic symphony composed of space and time itself, dancing together in eternal harmony. Every single particle of matter gently bends and shapes the very structure of reality itself, creating ripples that spread through the fabric of everything that is. We ride the gentle contours of space-time itself, shaped lovingly by the presence of distant stars, carved tenderly by the invisible shadows of mass that surround us always. Even those seemingly empty spaces between galaxies are delicately woven with invisible curvature, stretched and shaped by the slow, patient expansion of our cosmos. You, a single, precious mind floating through space and time, are not separate from this vast geometry. You are a ripple in the cosmic fabric. Your heartbeat actually bends the structure of space-time itself. Your very presence shapes reality, just as surely as reality shapes you. General relativity whispers to us softly that we belong to the cosmos completely, returning home to the infinite embrace of curved space-time itself. To speak of our universe without geometry, my gentle friend, would be like trying to describe a hauntingly beautiful melody without ever mentioning its pitch. Geometry is the very architecture of physical law itself, the blueprint upon which all of reality is lovingly constructed in the tender embrace of general relativity. It's infinitely more than just a backdrop. It is an active, living participant in the unfolding story of our cosmos, responding with exquisite sensitivity to every whisper of mass and energy. Where the classical physics of earlier centuries once treated space and time as rigid, general relativity offers us something infinitely richer. Space and time are lovingly merged into a single, unified entity, space-time, whose shape and curvature flow and dance dynamically, determined moment by moment by the beautiful contents of the universe itself. The concept of space-time curvature is central to everything we're exploring together tonight. In our precious daily lives, space seems wonderfully flat and predictable. These are the local approximations that comfort us. But on cosmic scales, or in the profound presence of strong gravitational fields, space and time begin to bend, until reality itself becomes something almost too beautiful and strange to comprehend. Curved space-time, dear friend, is a literal, precise description of how the distances between points and the precious intervals between events vary and dance due to the presence of mass and energy throughout the cosmos. The fabric of space-time itself can exist in states of flatness or curve into configurations of breathtaking complexity and grace. Space-time does not curve into some higher dimensional space that we could observe directly with our eyes. Its curvature is intrinsic, woven into its very being. This is where Riemannian geometry becomes our gentle guide. This mathematical framework provides the tools for understanding curved surfaces of any dimension. In general relativity, the geometry of space-time is lovingly described using a specific kind of curved, four-dimensional manifold. 3 dimensions of space, weaving together with 1 dimension of time. The curvature of this cosmic manifold is encoded in a mathematical object of profound beauty, known as the metric tensor, which specifies with exquisite precision how distances and times are measured locally at each precious point in space-time. Unlike in Euclidean geometry, the space-time metric in general relativity is dynamic and alive, constantly influenced by the ever-changing distribution of mass and energy throughout the cosmos. The shape of space-time affects everything, absolutely everything, that moves through its curved embrace. Planets following their eternal orbits, beams of light traveling across billions of years, even time itself, all dance to the rhythm set by space-time's geometry. The geodesics, those paths of least resistance, the straightest possible routes through curved space-time, are determined entirely by the geometry described by the metric tensor. In flat, familiar space, a geodesic is simply a straight line. But in the curved space-time of our universe, geodesics become the trajectories that freely falling objects follow naturally. What is profoundly moving about this framework is that objects in free fall are not being pushed or pulled by some external force. Instead, they are simply following the geometry that has been laid out for them. When our Earth orbits the Sun, it is following a geodesic, the most natural path possible, through the curved space-time created by our Sun's loving mass. If we could somehow magically eliminate the Sun, Earth would shoot off in a straight line, according to the now flat geomet of empty space-time. Different configurations of mass and energy throughout the universe generate different curvatures. A small planet creates a gentle, subtle well in space-time. A massive star produces a much deeper gravitational well. A black hole represents a region where curvature becomes so extreme that geodesics spiral inward toward the center, and no paths, no possible routes, lead back out to the wider universe. These curvatures have measurable, observable consequences that ripple through every aspect of our cosmic experience. Light from distant stars bends gracefully around massive objects, creating the beautiful phenomenon of gravitational lensing. Space-time curvature is not localized. Instead, it propagates, spreading outward like ripples on a cosmic pond. A sudden change in the arrangement of mass, such as two black holes merging, sends gentle ripples through the entire fabric of space-time. These ripples, known with beautiful precision as gravitational waves, are tiny distortions in the geometry of reality itself, traveling outward at the speed of light. Their detection, first achieved by the magnificent LIGO Observatory in 2015, provided direct, undeniable evidence. One of the most elegant and deeply satisfying features of general relativity is that it eliminates the need for that troubling concept of action at a distance. The influence of mass on space-time geometry propagates at a finite, measurable speed, no faster than light itself. The behavior of time within curved space-time reveals another profound consequence of this geometric understanding. The rate, at which time passes, depends intimately on the gravitational potential. A clock positioned closer to a massive body ticks more slowly and gently than one situated farther away. This effect, called gravitational time dilation, has been confirmed repeatedly through careful experiments with atomic clocks placed at different altitudes on Earth, carried in satellites orbiting high above. Time, as lovingly described by general relativity, is a coordinate that bends, stretches, and flows in ways utterly dependent on the geometry that surrounds it. Space-time geometry also dictates the very structure and architecture of our universe on the largest possible scales. by applying Einstein's elegant equations to the cosmos as a unified whole. Cosmologists derive beautiful models that describe how our universe expands, curves, and evolves. These models predict that space-time itself can have global curvature, existing in states that are flat, open, or closed. Observational evidence from the cosmic microwave background suggests that our universe is very nearly flat. But even this apparent flatness may be just a local property of our observable universe. Space-time geometry underpins the development of cosmological inflation, that rapid, dramatic expansion of the universe in its earliest, most precious moments. The subtle geometry of space-time during those first moments of inflation left its permanent imprint on the cosmic microwave background. Space-time geometry responds not only to ordinary matter, but also to energy in all its forms. This includes the mysterious, dark energy, that strange, invisible presence that permeates what we think of as empty space, accelerating our universe's expansion with each passing moment. Dark energy contributes to the curvature of space-time by creating a kind of gentle, repulsive effect on cosmic scales, pushing space itself to expand faster and faster. The discovery of this accelerated expansion in the late 1990 seconds revealed that geometry and energy are inextricably linked. Despite its remarkable successes, the geometric description of gravity raises profound questions. At the center of every black hole lies a singularity, a point where space-time curvature becomes infinite, where the familiar laws of general relativity break down completely. Physicists suspect that a quantum theory of gravity will eventually replace our classical picture, revealing a more granular, more fundamentally discrete structure of space-time itself. Nevertheless, the geometric vision of general relativity remains unmatched in its elegant beauty and precise accuracy. It reduces gravity to nothing more than a change in the living fabric of existence itself. Space-time is not simply the arena in which physics takes place. You are part of the geometry itself, an integral thread in the cosmic tapestry. Each breath you take, each beat of your faithful heart, gently shifts the curvature of the world around you. Every object in the universe contributes its unique presence to the ever-changing shape of space-time. You belong here, in this curved cosmos, as an essential participant in the ongoing creation of reality itself. Chapter 3: Time Dilation and Gravitational Time Travel. Even in the precious stillness of this moment, you are never truly still, dear friend. You are always lovingly embedded, always gently woven into the living fabric of something infinitely greater than yourself. You are part of the cosmic shape that holds distant stars in their celestial embrace, that guides vast galaxies in their eternal spiral dance. You belong here, in this curved and beautiful universe that shapes you even as you help to shape it. Time, precious time, as we experience it in our daily lives, seems so beautifully universal, so comfortingly predictable. From our everyday perspective, time appears absolute, constant, evenly paced for everyone we know and love. But this comfortable understanding is actually a gentle illusion. In the profound truth revealed by general relativity, time is deeply, beautifully, mysteriously relative. It flows differently depending on your speed through space, your location in the cosmic geography, and the gravitational embrace that surrounds you. Time reveals itself to be as dynamic and wonderfully malleable as space itself. The result is a universe of breathtaking strangeness and beauty, where time can stretch like warm honey in sunlight, compress like a gentle accordion, and even lead to forms of travel that defy our most basic everyday intuition. The concept of time dilation emerges naturally and gracefully from the fundamental structure of space-time in general relativity. It describes with mathematical precision the way in which time passes at different rates for observers resting in different gravitational potentials or moving at different velocities through the cosmic fabric. This is not simply a theoretical quirk. It is a rigorously tested and measurable effect. In regions where gravity embraces more strongly, time ticks more slowly and gently compared to regions where gravity's touch is lighter. This means that a clock positioned near a massive planet or hovering in the profound gravitational presence of a black hole will accumulate less time, will age more slowly than one floating in the vast, peaceful emptiness of deep space. This slowing of time, this stretching of moments, is a fundamental consequence of how space-time itself is lovingly shaped by the presence of mass and energy. To understand why this remarkable phenomenon happens, one must look again at the beautiful relationship between mass and geometry that Einstein revealed to us. In general relativity, massive objects bend the space-time around them like cosmic sculptors, and this curvature affects both space and time with equal grace and precision. When a clock is placed deep within a gravitational well, it measures what physicists call proper time, the time experienced along a path through space-time that is curved more steeply. To an external observer positioned at a higher altitude, that same faithful clock appears to tick more slowly and peacefully. The deeper in a gravitational well any object finds itself resting, the more dramatically time stretches and elongates for observers outside that gravitational embrace. Even here on our gentle Earth, time dilation is measurable and real, and must be carefully accounted for in the modern technology that serves us every day. Atomic clocks, when flown on aircraft or placed at the tops of mountains, run slightly faster than their companions resting at sea level. The difference is tiny, but it is real and measurable. The global positioning system provides one of the most striking and practical demonstrations of this principle. GPS satellites orbit Earth at an altitude where gravity's embrace is weaker. As a result of this difference in gravitational potential, their internal clocks tick faster by approximately 45 microseconds per day compared to clocks resting peacefully on Earth. If this relativistic effect were ignored, GPS calculations would drift by several kilometers each day. Engineers carefully compensate for this relativistic effect, making precise adjustments that confirm not only the theory's remarkable accuracy, but also its practical necessity in our daily lives. Beyond these everyday implications, time dilation becomes truly dramatic. In the most intense gravitational environments our universe has to offer. In theory, if someone could hover just above the event horizon of a black hole, their personal time would pass incredibly slowly relative to someone floating far away in the peaceful emptiness of space. Hours passing for the distant observer might correspond to mere minutes, or even precious seconds, for the person positioned near that event horizon. In this profound sense, gravitational time dilation creates a natural form of one-way time travel, allowing a traveler to move into the future more quickly than those left behind in weaker gravitational fields. Time travel into the future is not only allowed by general relativity, it is actually unavoidable in certain cosmic scenarios. Another beautiful form of time dilation arises not from gravity, but from motion itself. According to special relativity, time also slows down for objects moving at extremely high speeds. The faster an object moves through space, the slower its internal clock ticks, compared to a stationary observer watching from a distance. This effect is called kinematic time dilation. Studies with high-speed particles racing through accelerators show that unstable particles moving near the speed of light decay more slowly, live longer. Time for these swift travelers stretches and elongates. This phenomenon has real-world manifestations that touch our daily experience. The muons, produced by cosmic rays high in Earth's atmosphere, decay rapidly under normal conditions and should not survive long enough to reach the ground. Yet they do reach us, because their incredible speed causes their internal clocks to tick slowly. This beautiful observation matches perfectly with the predictions made by Einstein's theory of relativity. These two types of time dilation, gravitational and kinematic, are often considered as distinct effects, but general relativity reveals their deeper unity. Both result from differences in the geometry of space-time, as experienced by different observers moving along different paths. When taken to extremes, time dilation raises profoundly intriguing possibilities. If a sufficiently advanced civilization could orbit close to a black hole without crossing the event horizon, they could in principle witness immense stretches of cosmic time unfold before them. The entire future history of the universe could unfold before their eyes, while they themselves barely aged at all. Returning from such a remarkable journey presents far greater challenges. Gravitational time travel cannot easily reverse itself. The equations of general relativity are beautifully time-symmetric in their mathematical structure, but the specific conditions necessary to travel backward in time remain elusive and possibly forbidden by deeper physical laws. Solutions to Einstein's elegant equations do exist. Mathematical constructs like the Gödel metric or closed time-like curves that allow for backward time travel in principle. But these require extraordinarily exotic conditions. Most physicists believe that some version of what Stephen Hawking called the chronology protection conjecture prevents these more exotic scenarios from manifesting in physical reality. Still, the forward direction of time travel remains fully compatible with everything we know about physics. It blurs the traditionally clear line between rigorous science and profound philosophy. If two observers age at dramatically different rates due to space-time curvature or high-velocity motion, what does it truly mean for them to share a moment together? Time dilation also forces us toward a fundamental reconsideration of causality itself. In a universe where time flows differently for different observers, the concept of simultaneity becomes beautifully relative, dependent on perspective and position. Events that appear perfectly simultaneous for one observer may occur at different times for another observer, moving at a different velocity or resting in a different gravitational field. This reflects the fundamental structure of reality itself. Light cones, those geometric descriptions of causal relationships, and the very flow of time itself all depend intimately on one's position and motion through the curved space-time fabric. There is no universal now, no single moment that encompasses all of existence simultaneously. Instead, there are only sequences of events connected by light signals and causal relationships. The universe is not like a single river of time. Instead, it is a complex, beautiful topography of space and time, curved and tilted by the presence of mass and motion. Every object traces its own unique path through this magnificent terrain. The passage of time is not dictated by some single universal clock. Rather, it unfolds along the world line of each individual traveler, your heartbeat, your thoughts, flowing like gentle streams through consciousness, all unfold along a curved thread of space-time that is absolutely unique to you. The universe reveals temporal flow as something far more flexible and dynamic, a dimension shaped by context, by position. Under the gentle guidance of general relativity, we are all travelers, not only through the three familiar dimensions of space, but through time itself. Each of us moving forward along our own private axis of duration, influenced by where we find ourselves resting and how fast we happen to be moving through the cosmic fabric. Time bends like light around massive objects. It stretches like elastic under extreme conditions. It folds and curves according to the gravitational landscape. The gentle ticking of a clock on your wrist is not a universal truth shared by all of existence. It is a beautifully local rhythm, a beat set by the specific gravitational curvature of your particular world and the unique motion of your individual journey through space-time. No two beings, no two moments, no two paths through the curved space-time fabric are ever truly identical. Each of us experiences a slightly different universe, a subtly different flow of temporal current, a gently different now that belongs uniquely to our individual world line. And yet, miraculously, we manage to share this experience, this curved, shifting, deeply connected, cosmic dance. We find each other across the relativistic gaps. We communicate and love and dream together despite the fact that our clocks tick at slightly different rates. We are all temporal travelers, each following our own curved path through the magnificent geometry of space-time. As you drift toward sleep now, dear friend, let yourself feel held by this beautiful understanding that your experience of time, your personal rhythm of heartbeats and breaths, is absolutely unique in all the universe. And yet, it connects you intimately to every other conscious being, following their own curved path through the loving embrace of space-time itself. Chapter 4: Freefall and the Equivalence Principle. To truly understand gravity as Einstein saw it, one must begin not with the distant majesty of stars, but with falling. Free fall became for Einstein the precious key that unlocked a hidden truth about the deepest nature of reality itself. In the comfortable world of Newtonian physics, an object in freefall is simply one that has been released from rest, allowed to move under the influence of gravity alone. It accelerates downward because a force, gravity itself, acts upon it relentlessly. But something mysteriously peculiar has always lurked within its apparent simplicity. Different objects, regardless of their mass, fall at exactly the same rate through empty space. A delicate feather and a heavy bowling ball, when dropped in a vacuum, fall together with perfect synchronization. In Newton's mathematical equations, this remarkable fact occurs because the object's mass appears on both sides of the force equation and cancels out with elegant precision. But Newton never truly explained why that cancellation happens. It was simply accepted as an observed fact. Einstein took that simple observation and gave it entirely new meaning. He recognized that the equality of inertial mass and gravitational mass is not just a mathematical coincidence. It is a profound clue. In Einstein's revolutionary view, this equality suggested something almost unthinkable, that gravity might not be a force at all in any traditional sense. Instead, what we interpret as gravitational force might be something far more subtle, fundamentally geometer. I see in nature. To explore this breathtaking idea, Einstein considered the experience of an observer sealed inside a falling elevator. Imagine yourself enclosed in a windowless elevator drifting in the vast emptiness of deep space. Suddenly, the elevator begins accelerating upward with steady force. You feel your body pressed firmly to the floor. It feels exactly like the familiar pull of gravity we know so well. Now imagine a second elevator, one that begins stationary above our Earth, then is cut loose, so it begins to fall freely toward the surface below. Inside that falling elevator, you would float like an astronaut, weightless and serene. This shared motion makes the force of gravity seem to disappear completely from your immediate experience. Einstein saw these two experiences, accelerating upward in empty space and falling freely in a gravitational field, as fundamentally, mysteriously equivalent. This profound insight became the essence of what he called the equivalence principle, the revolutionary idea that local experiments cannot distinguish between uniform acceleration and gravitational freefall. They are the same phenomenon viewed from different perspectives. From this elegant principle, Einstein began to construct an entirely new theory of gravity, not as a force that reaches across empty space, but as an intrinsic property of space-time itself. In this breathtaking new view, when you drop an object and watch it fall, it doesn't accelerate because some invisible force pulls it downward. Instead, it moves along the most natural path possible, a geodesic, through the curved landscape of space-time. The only reason you perceive it as falling is because you yourself are not in free fall. You, standing on Earth's surface, are actually being pushed upward, gently but constantly, by the ground beneath you. Gravity, in this revolutionary formulation, is not pulling things down toward Earth's center. Instead, surfaces like the ground beneath our feet are pushing objects away from their most natural trajectories through curved space-time. Astronauts in orbit around Earth feel perfectly weightless, not because there's no gravity affecting them, but because they are in continuous free fall. The familiar sensation of weight disappears completely when you're free to follow your natural geodesic through the curved geometry of space and time. The equivalence principle has been tested with extraordinary precision by generations of careful scientists. All objects fall identically, regardless of their material properties, so long as only gravity acts upon them. These painstaking experiments reinforce Einstein's core insight with beautiful consistency. Gravity is not fundamentally about forces acting on objects from a distance. It's about the natural shape of the paths that objects take when free to move through curved space-time. This profound understanding allowed Einstein to generalize special relativity into a broader, more comprehensive theory that could also describe acceleration and gravitational effects. Freefall became the fundamental key to unlocking how space-time responds to the presence of energy and mass throughout the universe. When Einstein presented his complete theory in 1915, the strange precession of Mercury's orbit emerged naturally and beautifully From the geometry of curved space-time around our sun, the bending of light around massive objects, the gradual slowing of time near massive bodies, the exotic dynamics of black holes, all followed logically and elegantly from this simple yet profound principle. What makes the equivalence principle so remarkably powerful is its beautifully local nature. It doesn't attempt to describe gravity everywhere throughout the universe at once. Instead, it focuses on what can be observed and measured in small regions of space-time. In these precious local regions, the laws of physics take exactly the same elegant form as in special relativity, only when comparing events at different locations, where the curvature of space-time varies from place to place, do the subtle effects of gravity begin to emerge. In this beautiful sense, general relativity becomes like a cosmic patchwork, a collection of locally flat regions sewn together by the gentle curvature that mass and energy create in the fabric of space-time itself. Even time becomes relative to the specific path an object takes through the curved landscape of space-time. A clock in free fall ticks at its own proper time, measured faithfully along its natural geodesic. It is only when we compare that freely falling clock to one that is not in free fall that we observe the beautiful difference in their rates. Gravity, therefore, is not acting directly on time itself. Instead, it shapes the paths through which temporal flow moves. Here on Earth, we feel the familiar force of gravity pressing us downward because we are being held up. From the perspective of general relativity, we are actually accelerating upward, constantly, relative to a freely falling reference frame. A satellite in orbit around Earth is actually the one experiencing no force whatsoever. It is simply coasting along its most natural geodesic through curved space-time. We here on the surface, feeling so solid and stationary, are actually the ones deviating continuously from that natural motion. The counterintuitive nature of this truth can feel unsettling at first. Gravity no longer pulls objects down toward planetary centers. Instead, the geometry of space-time guides all motion, and resisting that gentle guidance produces the familiar sensation of weight. The implications of the equivalence principle extend far beyond gravity itself. It has inspired countless attempts to unify general relativity with quantum mechanics. Some approaches in theoretical physics seek to explain space-time and gravitational effects as emergent phenomena arising from information theory, thermodynamics, or quantum entanglement at the most basic level. At the heart of all these considerations lies one simple, beautiful realization that falling freely is completely indistinguishable from floating weightlessly through empty space, and that what we once thought of as gravitational force is instead a gentle whisper embedded in the very structure of space and time. Every single time you drop an object, you are witnessing not a pull or attraction, but a path being followed, a quiet, ancient trajectory that was carved into the shape of the cosmos, long before consciousness arose to observe it. The falling object is not being acted upon by some external force. It is being released, set free to return to the geodesic line. It was always meant to follow through the curved space-time fabric. Perhaps we are all falling freely through a universe that bends gently around us, mostly unaware of the deeper geometric structure beneath our feet. And in that cosmic falling, we are never truly alone. We are part of a vast pattern that is constantly unfolding, a living geometry that was written into the structure of reality long before we knew how to look for it. Chapter 5. Curved Paths in a Curved Universe. Motion through the vast spaces of our cosmos has always carried with it an intuitive simplicity. Humanity has long imagined with comfortable certainty that objects left undisturbed move in perfectly straight lines. Any deviation from that straight line motion must result from some applied force acting from outside. This fundamental idea formed the strong backbone of classical mechanics. But Einstein's theory of general relativity completely replaces this familiar mechanical picture with something far more beautiful and profound, a geometric vision of reality that changes everything. Objects do not move through space because they are pushed or pulled by external forces. They move because they are following the fundamental structure of space-time itself. A planet orbiting its star, a comet tracing its elongated elliptical path. All are following the same basic principle. They are moving along geodesics, the straightest possible paths through the curved geometry of space-time. In this breathtaking new understanding, what appears to us as curved motion is actually the most direct route possible through the warped space-time created by the sun's immense mass. The curvature we observe in planetary orbits is the natural consequence of space-time itself being curved by the presence of mass and energy. Every massive object creates its own unique curvature in the fabric of space-time, like placing weights of different sizes on a stretched rubber sheet. Each creates valleys and hills that guide the motion of everything else in their cosmic neighborhood. The more massive an object, the deeper and more pronounced the curvature it creates. Our sun creates a substantial well in space-time, deep enough to guide the orbital paths of all the planets. Jupiter creates its own smaller but significant curvature, influencing the paths of its many moons. Even our Earth creates its own gentle curvature in space-time, keeping our moon in its faithful orbit. But the true beauty of this geometric understanding reveals itself when we consider motion at the largest scales. Here, space-time curvature becomes not just a local phenomenon, but a cosmic architecture that shapes the evolution and structure of everything that exists. Galaxies themselves follow geodesics through the large-scale curvature of space-time. Their mutual gravitational influence, their dark matter halos, their interactions with the mysterious dark energy, all contribute to the cosmic geometry. galaxy clusters create such profound curvature in space-time that they act as cosmic lenses, bending and focusing light from even more distant galaxies behind them. This gravitational lensing effect allows us to see farther into the universe than would otherwise be possible. The expansion of the universe itself is also a manifestation of space-time geometry on the grandest possible scale. Even light, that pure energy racing through space at the ultimate speed limit, follows geodesics through curved space-time. When light passes near a massive object like our sun, it follows a curved path, not because it is being pulled or deflected by a force, but because it is taking the straightest possible route through the curved space-time around the sun. This bending of light was one of the first dramatic confirmations that space-time itself is curved by mass and energy. Gravitational waves, those ripples in space-time itself, represent the ultimate expression of geometry in motion. When two black holes spiral into each other, they create disturbances in space-time that spread throughout the universe. These waves are literally ripples in the fabric of space and time. They represent space-time geometry made dynamic. The paths that objects take through this curved universe reveal the intimate connection between matter and geometry. Every particle, every planet, contributes to the overall curvature, while simultaneously responding to it. Even the quantum vacuum contributes to space-time curvature through its intrinsic energy density. This vacuum energy may be responsible for dark energy. The paths through curved space-time also reveal the deep connection between motion and time. Objects following different geodesics through regions of different curvature experience time at different rates. A satellite in high orbit around Earth ages faster than we do on the surface. Particles in accelerators are not following natural geodesics. Instead, they are being forced away from their natural straight-line paths through space-time. The most extreme example of curved paths in our universe occurs near black holes, where space-time curvature becomes so intense that geodesics can form closed loops. Light itself can orbit a black hole at the photon sphere. Inside the event horizon, all geodesics lead inexorably toward the central singularity. The curvature has become so extreme that even the fastest possible motion cannot overcome the geometric constraints. The beauty of this geometric understanding extends beyond gravity to suggest deep connections with other fundamental forces. Some theories propose that all forces might ultimately be understood as different aspects of space-time geometry. In these unified field theories, particles don't experience separate forces at all. Instead, they follow geodesics through higher dimensional curved spaces. As you drift towards sleep tonight, let yourself imagine the curved paths you are following through space-time. Your body, resting peacefully, is actually racing through space at tremendous speed. All of these motions represent geodesics through the curved space-time of our universe. You are an active participant in the cosmic geometry, helping to shape the very space-time through which you travel. Every heartbeat, every breath, contributes in its own small way to the curvature of space-time around you. You are both sculptor and sculpture in the ongoing creation of cosmic geometry. Rest now in the knowledge that your path through this curved universe is as natural and necessary as the orbit of planets. You belong here, following your own unique geodesic through the magnificent, ever-changing geometry of existence. They all follow these curved trajectories, not because some mysterious force bends them away from their intended paths, but because space-time itself is lovingly curved, and they are simply tracing the straightest possible paths within that curved cosmic landscape. In general relativity, the familiar concept of a straight line is gracefully generalized to something called a geodesic. A geodesic represents the path through space-time that a freely falling object follows. In flat space-time, a geodesic remains identical to the straight line we learned about in school geometry. But in the magnificent presence of mass and energy, space-time becomes beautifully curved, and the straightest possible path becomes a more complex, more graceful trajectory. This curvature is not an intrinsic property of the moving object itself, but rather a fundamental characteristic of the space through which it moves. Imagine placing a smooth marble on a stretched rubber sheet. If the sheet remains perfectly flat, the marble will roll in a completely straight line. But if you place a heavy ball somewhere on that sheet, it will create a gentle deformation. Now, if you roll the marble again across this altered surface, it will spiral gracefully toward the depression. No external force acts laterally on the marble. It simply follows the shortest, most natural path available in this new curved geometry. This analogy captures the essential wisdom of what general relativity proposes about our cosmos. Gravity is not a force reaching across empty space, but rather a natural feature of the cosmic landscape itself. The presence of mass alters the fundamental shape of space-time, and objects respond by following the gentle contours of that reshaped reality. In our actual universe, this curvature occurs in 4 magnificent dimensions, 3 of familiar space and 1 of mysterious time, and is described with mathematical precision by something called the metric tensor. When mass or energy is introduced into this elegant framework, the curvature changes responsively, and the geodesics adapt accordingly with perfect grace. A star does not tug on a planet with invisible strings. It reshapes the space-time around it like a cosmic sculptor. The orbit of Mercury provides a beautifully concrete example of this profound phenomenon. For centuries, careful astronomers noted that Mercury's orbit shifted slightly with each revolution around our Sun, a tiny but persistent mystery. This anomaly remained stubbornly unaccounted for until Einstein applied his revolutionary field equations to the problem when he modeled the curvature of space-time near our Sun. and calculated Mercury's path as a geodesic moving through that curved geometry. The unexplained precession appeared naturally in the mathematics. It was one of the first major triumphs of general relativity. Curved space-time also affects light in ways that seem almost magical. Although photons are completely massless, they still travel along geodesics called null geodesics. When a beam of light passes near a massive object, its path bends gracefully because space-time is curved in such a way that the straightest possible path is no longer straight in the familiar sense. This gentle bending of light was famously confirmed during the historic 1919 solar eclipse, validating Einstein's breathtaking predictions. The fundamental geometry of space-time determines the entire magnificent structure of cosmic motion, the graceful rotation of galaxies, the gradual evolution of our universe itself, all arise from these curved pathways, lovingly shaped by mass and energy. Chapter 6. Light bends and echoes through gravity. For much of human history, light was thought to be the fastest and most perfectly straight-moving phenomenon in our universe, untouched by gravity or matter. In the comfortable world of Newtonian physics, gravity affected only objects possessing mass, and light, having no mass whatsoever, should have remained forever unbent. But general relativity changed that understanding forever. In Einstein's revolutionary framework, light travels through space-time itself, that dynamic four-dimensional fabric that breathes and curves with the presence of matter and energy. And when that space-time is curved, the path of light must curve as well. The effect occurs not because gravity pulls on light in any traditional sense, but because the space-time through which light moves is itself gently bent and shaped. Light always moves along what physicists call null geodesics, saying possible routes through curved geometry. When light encounters the curved space-time around a massive star, it simply follows the most direct path available. This phenomenon, known as gravitational lensing, transforms massive cosmic objects into natural telescopes. Galaxy clusters create such profound curvature in space-time that they can magnify and distort light from even more distant galaxies behind them. The bending of light also reveals the presence of otherwise invisible matter. Dark matter can be detected through its gravitational lensing effects. When light climbs out of a gravitational well, it loses energy and becomes redshifted, stretched toward longer, redder wavelengths. This gravitational redshift has been measured with exquisite precision. Conversely, when light falls deeper into a gravitational well, it gains energy and becomes blue-shifted. The most extreme examples of light's interaction with curved space-time occur near black holes, where curvature becomes so intense that it creates regions from which light cannot escape. The event horizon represents the boundary just outside the event horizon. At what's called the photon sphere, light can orbit the black hole in circular geodesics, the image of a black hole's shadow, first captured by the Event Horizon Telescope in 2019, shows this interplay between light and extreme space-time curvature. Gravitational waves also affect light in profound ways. As a gravitational wave passes through a region of space, it alternately stretches and compresses distances. This changing geometry affects the paths that light rays follow. The detection of gravitational waves represents the ultimate confirmation that space-time itself is dynamic. Even the expansion of the universe affects light in ways that reveal space-time's global geometry. As light travels across cosmic distances, the expansion of space stretches its wavelength, creating the cosmological redshift. The cosmic microwave background provides the most distant light we can observe, stretched by 13 billion years of cosmic expansion. Through all these phenomena, light serves as our most faithful messenger, carrying information about the curved geometry of space-time across the vast distances of our universe. Every photon that enters our eyes has followed a geodesic through the curved space-time of our cosmos. Every act of seeing connects us directly to the curved structure of our universe. The light reaching us from distant stars and galaxies has been lovingly guided by space-time's curvature. The gentle bending of light is not limited to stars glimpsed during rare eclipses. It happens constantly throughout our cosmos, a continuous cosmic dance between light and curved space-time. Galaxies and galaxy clusters act as gravitational lenses, distorting and magnifying the precious light from even more distant objects. Sometimes this leads to visible effects of stunning beauty, like Einstein rings. Gravitational lensing has become one of the most powerful and elegant tools in astrophysics and cosmology. It can reveal the invisible presence of dark matter through its gravitational effects on light passing nearby. We can detect with precision how it distorts the paths of light around it. Gravitational lensing can affect the cosmic microwave background. The fields gently nudge the paths of individual photons, altering the distribution of temperature and polarization we observe today. Another profound consequence of curved space-time is the gravitational redshift of light. As light climbs out of a gravitational well, it loses energy by stretching its wavelength like a cosmic accordion. This shift toward longer, redder wavelengths is a direct prediction of general relativity and has been observed with remarkable precision. Gravitational redshift is not merely a theoretical curiosity. The precise clocks aboard GPS satellites experience both special relativistic time dilation and general relativistic shifts. As a result, signals transmitted from these satellites are slightly but measurably redshifted compared to ground-based clocks. Engineers must continuously correct for this shift. Another elegant and testable prediction of general relativity is gravitational time delay, sometimes called the Shapiro delay. When light passes near a massive object, the time it takes to traverse that curved path is subtly increased. This delay arises because the geometry of space-time near massive objects is stretched and elongated. This remarkable effect has been confirmed through radar signals sent to planets and reflected back to Earth. Gravitational time delay has also been observed in more distant and exotic settings. When light from a brilliant quasar or exploding supernova is gravitationally lensed by an intervening galaxy, it can take multiple curved paths through space-time to reach our telescopes. These echoes through gravity, these temporal duplications of cosmic events, offer unique opportunities to measure the expansion rate of our universe. Even gravitational waves interact with light in measurable and profound ways. In detectors like LIGO, the length of each arm changes slightly, but measurably, causing the laser beams to shift in phase when they recombine. This intricate interplay between light and space-time makes it possible to use individual photons as messengers, carrying information about the curved geometry they have traversed during their cosmic journey. Every beam of starlight carries with it a precious memory of the space-time through which it has traveled. The most dramatic applications of these profound ideas emerges in our study of black holes. Near a black hole, light itself can become trapped in stable orbit, following circular geodesics around the gravitational monster. There exists a precise region known as the photon sphere, where light can circle the black hole endlessly in perfect balance. These photon spheres contribute significantly to the visual appearance of black holes, and were crucial in generating the distinctive shadow observed in the Event Horizon Telescope's historic image. The light that barely grazes the photon sphere before escaping carries with it a distorted and amplified image of the surrounding space-time. Multiple nested images can be formed as light orbits the black hole several times before finally emerging. These layers of light encode an intricate map of the black hole's geometry, a detailed fingerprint of space-time under the most extreme conditions our universe can create. The expansion of our universe causes distant galaxies to appear redshifted, their ancient light stretched as space itself expands. This cosmological redshift differs in origin from gravitational redshift, but it represents another profound way in which light reflects the dynamic nature of space-time itself. Together, these remarkable phenomena reveal a profound picture of light, not as a passive traveler moving through empty space, but as an active participant in the ongoing story of our universe. Light moves through space-time with exquisite grace, but it also responds to space-time's gentle embrace with profound sensitivity. The photons we detect in our telescopes are faithful witnesses to curvature. Every star we see twinkling in the night sky comes to us through a winding, curved, and gravitationally textured path through space-time. And yet, light still arrives with remarkable fidelity, bringing us precious echoes of ancient events. It is light that allows us to see the beauty of our cosmos, but more profoundly, it is light that allows us to truly know and understand our place within it. Perhaps, then, the gentle bending of light is not merely a demonstration of gravity's far-reaching influence, but a quiet reminder that in the deepest fabric of reality, even the straightest thing we know yields gracefully to the shape of existence itself. Chapter 7. Black Holes, the ultimate curves in space-time. Among all the remarkable predictions of general relativity, few are as startling, extreme, or counterintuitive as the black hole. Black holes arise as natural, unavoidable solutions to the field equations. They represent the ultimate expression of gravitational curvature, regions where space-time is no longer gently bent like rolling hills, but folded so severely that all possible paths lead inexorably inward, and nothing, not even light itself, can escape their gravitational embrace. The existence of black holes was first hinted at long before Einstein's time. Visionary scientists like Jean Michel and Pierre-Simon Laplace speculated that a sufficiently massive object could possess an escape velocity greater than the speed of light itself. It wasn't until Carl Schwarzschild in 1916 provided the first exact solution to Einstein's field equations that the black hole concept began to take more rigorous mathematical shape. This solution revealed a critical radius, now called the Schwarzschild radius, within which the curvature of space-time becomes so intense that all geodesics converge inward toward the center with absolute inevitability. This boundary, this point of no return, is known as the event horizon. It is purely a one-way threshold in the geometry of space-time itself. Once crossed by any object or signal, no information can ever reach the outside universe. According to classical general relativity, the collapse of matter continues relentlessly inward, compressing into a single point of infinite density, a mathematical singularity where the normal rules of physics break down completely. At this singularity, the curvature of space-time itself becomes infinite. Black holes are absolutely real astrophysical objects. They form naturally when the most massive stars reach the end of their nuclear life cycles. If the remnant core remaining after the star's death is sufficiently massive, no known force can halt the catastrophic collapse. The result is a stellar mass black hole, typically several times the mass of our life-giving sunday, but occupying a region only a few kilometers wide. One key method involves studying accretion disks, those spiraling maelstroms of gas and dust that fall inexorably toward a black hole, emitting intense radiation, particularly in the high-energy X-ray spectrum. Another major breakthrough came with the direct observation of gravitational waves. When two black holes spiral toward one another, they generate gravitational waves that travel outward at the speed of light. In 2015, The LIGO detectors achieved the first direct observation of such a signal, marking the dawn of gravitational wave astronomy. Then, in 2019, came the first actual image of a black hole's shadow, captured by the Event Horizon Telescope. This composite image of the supermassive black hole at the center of galaxy M87 showed exactly what theory predicted: a dark, central region, the shadow of the event horizon itself, surrounded by a brilliant glowing ring of superheated matter. Black holes vary dramatically in size and mass, from the stellar mass variety to the supermassive giants found lurking at the centers of galaxies. The origin of these supermassive black holes remains one of the great open questions in astrophysics. Some galaxies contain what astronomers call active galactic nuclei, regions where matter falling into a supermassive black hole releases enormous amounts of energy. These objects, known as quasars, when viewed from great distances, are powered by the conversion of gravitational potential energy into pure radiation. The physics near black holes also challenges our deepest understanding of information and entropy. In the 1,970 seconds, Stephen Hawking made a startling discovery. Quantum effects near the event horizon cause black holes to emit radiation, now known as Hawking radiation. Hawking radiation suggests that black holes can slowly lose mass and eventually evaporate completely. This leads to what's known as the black hole information paradox. If Hawking radiation appears purely thermal, with no information content, then information appears to be permanently lost when a black hole finally evaporates. This would contradict a core principle of quantum mechanics, that information must always be conserved in physical processes. Resolving this paradox represents a major challenge in theoretical physics. Near the event horizon, time for an outside observer appears to slow to a complete halt as an object approaches the horizon. This apparent discrepancy is a real and unavoidable consequence of the extreme geometry of curved space-time near the event horizon. In theoretical extensions of general relativity, solutions like the Kerr metric describe rotating black holes. These rotating black holes exhibit complex structures including ergospheres. Some theoretical solutions even allow for hypothetical wormholes, tunnels through space-time that might connect widely separated regions of the universe. Black holes are not science fiction fantasies. They are testable, observable objects, deeply integrated into our understanding of how the universe works. They serve as the ultimate laboratories for physics, where our theories are pushed to their absolute limits. Their formation, evolution, and violent interactions shape the structure of galaxies, emit gravitational waves that ripple across the entire observable universe. They also serve as boundaries, places where the geometry of reality becomes so extreme that our normal understanding breaks down. As you rest tonight, let yourself contemplate these cosmic mysteries. Black holes represent both the most extreme physics our universe can create and profound reminders of the limits of human knowledge. They are precious portals to deeper understanding, gateways to more refined theories. They represent the ultimate expression of space-time curvature, the final answer to what happens when gravity is taken to its most logical extreme. Chapter 8. Gravitational waves, ripples in the fabric of reality. In the elegant framework of general relativity, mass and energy shape the geometry of space-time with exquisite precision. The mathematical equations also implied something far more dynamic and profound. If space-time could bend, then it could also ripple. And if those ripples could propagate outward at the speed of light, then gravity itself might carry energy across the vast cosmos in the form of waves. These hypothetical distortions are known as gravitational waves. They are waves of space itself, oscillations in the very metric that defines distance and duration throughout the universe. As they pass through any region of space-time, they stretch and compress the fabric of reality itself. Gravitational waves pass through dust, gas, planets, even entire stars with near impunity, preserving the pristine imprint of the cataclysmic events that produced them. Einstein first predicted the existence of gravitational waves in 1916. The generation of gravitational waves requires the acceleration of massive objects. Objects must accelerate asymmetrically, changing the shape of the gravitational field around them in complex ways. A pair of stars orbiting each other sends out gentle ripples in the very fabric of space-time. The more massive the objects, and the faster they move, the stronger the resulting gravitational wave signal becomes. The most powerful gravitational waves come from the most violent and energetic processes our universe can produce. Black hole mergers, neutron star collisions, core collapse supernovae. For many decades, the evidence for gravitational waves remained tantalizingly indirect. In 1974, astronomers Russell Hulse and Joseph Taylor made a remarkable discovery: a binary pulsar system containing two neutron stars. Over years of careful observation, they watched as the orbit gradually shrank. The rate of this orbital decay matched perfectly the predictions of general relativity. Assuming that gravitational waves were being emitted, this discovery earned them the Nobel Prize in Physics. That profound moment finally arrived in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made history with a detection. Detectors recorded the unmistakable passage of a gravitational wave sweeping across our planet. The signal matched the theoretical waveform predicted for two black holes, merging in a cosmic collision over 1 billion light-years away. In just a fraction of a second, these black holes coalesced, releasing a burst of gravitational radiation so powerful that it briefly exceeded the total energy output of all the stars in the observable universe. Yet, its effect had diminished to almost nothing, changing the length of LIGO's 4-kilometer arms by less than 1,000th the diameter of a proton. LIGO achieves this impossible precision through laser interferometry. A coherent beam of laser light is carefully split and sent down 2 perpendicular arms extending for kilometers. If a gravitational wave passes through the detector, it slightly stretches one arm while simultaneously compressing the other, creating a telltale interference pattern in the recombined light that reveals the wave's presence. Since that historic first detection, dozens more gravitational wave events have been observed. In 2017, the detection of a neutron star merger designated GW170817 marked another watershed moment in astronomy. This event was observed not only through gravitational waves detected by LIGO and Virgo, but simultaneously across the entire electromagnetic spectrum by telescopes around the world. This marked the true beginning of multi-messenger astronomy, where gravitational waves and electromagnetic observations combine. Gravitational waves have also opened entirely new avenues for testing general relativity under the most extreme conditions. So far, the results have been remarkably consistent with general relativity. Current observatories like LIGO in the United States and Virgo in Europe are continuously being upgraded. New detectors such as KAGRA in Japan and the planned Einstein telescope in Europe will dramatically increase our ability to detect weaker signals. Perhaps even more transformative will be LISA, the Laser Interferometer Space Antenna, scheduled for the 2030 seconds. LISA will consist of 3 spacecraft orbiting our Sun, detecting gravitational waves with periods far longer than ground-based instruments can possibly measure. This space-based observatory will open an entirely new window on the gravitational wave universe, capable of detecting signals from supermassive black hole mergers at the largest scales. Scientists hope to detect what's called the gravitational wave background, a persistent cosmic hum composed of gravitational waves from countless unresolved sources. This background signal, if successfully detected, would serve as a cosmic fossil, preserving information about epochs in cosmic history otherwise completely inaccessible. Pulsar timing arrays are already actively seeking this elusive signal. What makes gravitational waves so profoundly remarkable is that they extend our senses in ways never before possible. Gravitational wave astronomy is not simply a replacement for electromagnetic observations. It represents an entirely new sense for exploring our cosmos. It is like suddenly gaining the ability to hear the universe for the first time. The gravitational wave signals we now routinely detect were always there. Each gravitational wave detection preserves a fossil record of motion in space-time itself. Gravitational waves tell us directly how they moved and changed. They carry their stories directly and unedited across billions of light years. In the coming decades, these gravitational wave observations may help answer some of the deepest questions in all of physics. They may provide crucial clues about how matter behaves at nuclear densities. They might even reveal violations of general relativity. deviations that point toward new physics, beyond Einstein's remarkable but perhaps incomplete theory. As you drift toward sleep, dear friend, let yourself feel connected to this cosmic symphony, this constant rain of gravitational waves washing over our planet from the most violent events throughout the universe. These waves pass through your body countless times each day, carrying with them the stories of cosmic catastrophes. You are intimately connected to the most extreme physics our universe can create. Rest peacefully, knowing that even as you sleep, sensitive detectors around the world continue listening to space-time's gentle songs. Gravitational waves may one day guide us toward unifying general relativity with quantum mechanics. The ripples that travel through space-time are not loud. They pass quietly, gently, stretching the dimensions of space and time as they go. And yet, in those subtle distortions lies an entire narrative. Gravitational waves are silent messengers, but they carry deep truth that sometimes the cosmos whispers. And if we listen carefully enough, we can feel it moving. Chapter 9. Testing Einstein. How we know it's true. A theory is only as powerful as its predictions, and only as trustworthy as the experiments that verify them. When Albert Einstein published General Relativity in 1915, he offered not just a reinterpretation of gravity, but a radical reshaping of our understanding of space, time, and the geometry of the universe. Relativity made specific, testable predictions about the behavior of light, the motion of planets, the ticking of clocks, and the transmission of gravitational influence. Over the next century, these predictions faced one of the most rigorous programs of empirical scrutiny in science. 1919. Eclipse. O prediction. Light bends near massive bodies because mass curves space-time. O test. During a total solar eclipse, Arthur Eddington's teams photographed stars near the sun's edge. When the sun's glare was blocked, the stars appeared displaced outward. Oh, the measured bending matched Einstein's calculation, shifting relativity from speculation to observable reality. Mercury's perihelion precession. Oh, puzzle. Mercury's orbit precessed slightly each revolution. Newtonian gravity explained most, but not all. O resolution. Einstein's equations for the sun's curved space-time yielded the missing 43 arcseconds per century, turning a stubborn anomaly into a precise success. Gravitational time dilation. O claim. Time runs slower in stronger gravity. O tests. The 1,960-pound Rebka experiment measured the frequency shift of gamma rays over a building height drop, matching relativity's prediction. O atomic clocks on airplanes, mountaintops, and satellites tick at measurably different rates. O GPS must correct for both special and general relativistic effects. Without these nanosecond-level adjustments, positions would drift by kilometers per day. Binary pulsars. Indirect waves. Oh, the Hulse-Taylor pulsar, 1974, revealed orbital decay exactly as predicted, if the system loses energy to gravitational waves, providing strong indirect evidence decades before direct detection. Additional pulsars have reinforced these results in strong field regimes. Gravitational lensing. Massive objects bend light, producing arcs, rings, and multiple images. Observations align with simulations from Einstein's equations. Time delays between lensed images of variable sources. For example, quasars encode space-time curvature and test relativity on cosmological scales. Black hole shadows. In 2019, the Event Horizon Telescope imaged the supermassive black hole in M87. The bright asymmetric ring and central shadow matched predictions for light lensed near an event horizon, confirming relativity in extreme gravity. Gravitational wave astronomy becomes. The more important it becomes to probe its ultimate limits with exquisite precision. This search is not driven by doubt about Einstein's achievement, but by insatiable curiosity about what lies beyond our current understanding. What makes Einstein's work truly endure is not merely that it has passed so many rigorous tests, but that it invited so many tests in the first place. General relativity guided the design of satellites, observatories, and ambitious missions decades before the necessary technology existed to build them. And when our instruments finally caught up to Einstein's vision, the universe behaved exactly as the mathematical equations had predicted. That a single human mind working on Earth once peered deeply into the nature of geometric reality and found the entire universe written there in mathematical language, waiting to be discovered. And perhaps that represents the truest test of Einstein's revolutionary theory. Not only that it proves accurate in its predictions, but that it makes reality itself more intelligible and beautiful. Chapter 10. The Edges of Understanding, where relativity meets quantum physics. General relativity and quantum mechanics stand as the two towering pillars of modern physics. General relativity describes the realm of the very large with breathtaking scope. Quantum mechanics rules the mysterious realm of the very small with equal authority. Each theory works extraordinarily well within its own natural domain, but they remain stubbornly incompatible with one another in extreme environments, such as the theoretical center of a black hole or the first mysterious moments following the Big Bang. Both theories must apply simultaneously and seamlessly, and when physicists attempt to bring them together mathematically, deep contradictions emerge. General relativity treats space-time as fundamentally continuous and smooth, a classical theory in the deepest philosophical sense. Quantum mechanics introduces a fundamental probabilistic nature into reality itself. It describes a reality built from indivisible units, governed by inherent fuzziness and uncertainty, bringing these two radically different worldviews together. Quantizing the smooth geometric fabric of space-time itself proves immensely difficult. One of the earliest approaches was quantum field theory in curved space-time, which treats matter and radiation as quantum fields, but keeps gravity itself classical and non-quantum. This semi-classical approximation has achieved success in limited domains, such as explaining Hawking radiation. A complete quantum theory of gravity would need to treat space-time itself as fundamentally quantized. String theory represents one such candidate for unification. It proposes that the fundamental constituents of our universe are one-dimensional strings, vibrating at different characteristic frequencies. These strings naturally include a graviton among their vibrational modes, suggesting that gravity itself might emerge naturally from the underlying dynamics of string vibrations. String theory also predicts the existence of additional spatial dimensions. Another promising approach is loop quantum gravity, which attempts to quantize space-time directly without requiring extra dimensions. In this elegant model, space-time emerges as a network of finite loops representing quantum geometry itself. Loop quantum gravity predicts that space and time are genuinely discrete at the incredibly tiny Planck scale. In this picture, the smooth space-time we experience emerges as an approximation. Both string theory and loop quantum gravity attempt to accomplish the same profound goal. They seek to describe a complete quantum version of gravity that naturally reduces to Einstein's general relativity on large scales. Yet neither theoretical framework has achieved experimental confirmation. The effects of quantum gravity are expected to be extraordinarily subtle, only becoming significant near singularities. Testing these revolutionary ideas directly would require energy scales far beyond anything currently accessible through particle accelerators. As you rest tonight, dear friend, let yourself contemplate this profound mystery at the heart of physics, at the boundary between the quantum world of atoms and the curved space-time of gravity. New physics awaits. Discovery. Sleep peacefully, knowing that brilliant minds around the world continue working to bridge this fundamental gap. Some visionary theorists propose that quantum gravitational effects could leave subtle traces in the cosmic microwave background, or perhaps in high-energy astrophysical phenomena like mysterious gamma-ray bursts. Others hope that tiny violations of known symmetries might offer precious clues about the quantum nature of space-time. Even the gravitational waves we have already detected from black hole mergers could someday carry faint imprints of quantum corrections. Another profound area of tension lies in the black hole information paradox. According to quantum mechanics, information about any physical system is never truly lost. Yet if black holes slowly evaporate through Hawking radiation, and that radiation appears purely thermal with no information content, then all information about the matter that once fell into the black hole seems to vanish forever. This directly conflicts with the sacred principle of unitarity in quantum mechanics. Resolving this fundamental paradox remains one of the deepest unsolved problems in all of physics. This possibility finds expression in the remarkable holographic principle, which suggests that all the information contained within any volume of space can be completely encoded on its boundary, much like a hologram. This revolutionary idea emerged from studies of black hole entropy particularly the groundbreaking work of Jacob Bekenstein and Stephen Hawking. These profound concepts hint at a radical possibility. Perhaps space-time is not fundamental at all, but rather emergent, arising from more basic quantum processes we have yet to comprehend. If this proves true, then general relativity would not represent a fundamental theory of nature, but rather an effective approximation. In this revolutionary view, gravity, space, and time itself are not primary ingredients of the universe, but emergent phenomena arising far from quantum entanglement, information theory, or other foundational structures. This line of thought also suggests that time itself might not be fundamental. If space-time is truly quantized or emergent, then time may arise from correlations between quantum systems, a statistical property rather than an absolute dimension. The profound tension between general relativity and quantum mechanics is not a sign of failure in human understanding, but rather a signal of incompleteness. Yet nature in its awesome fullness encompasses both the curved space-time of gravity and the quantum behavior of matter and energy. Somewhere in the deep structure that underlies space-time and matter, these two descriptions must come together in perfect harmony. The search for this ultimate union represents a philosophical quest touching on the fundamental nature of existence. For now, we live in a universe where both theories remain true, but not yet unified. And in that profound silence, the next great theory patiently waits. Something beyond pure geometry and probability. Perhaps one day, future generations will look back at both general relativity and quantum mechanics as brilliant stepping stones. A theory that will not only describe the exotic physics at the edge of black holes and the mysterious birth of our cosmos, but will also explain why space, time, and existence themselves came to be. Closing, and now, my dear friend, if your eyes are still open and your mind remains curious about the mysteries of our cosmos, there's another fascinating journey waiting for you, just one gentle click away. But if sleep has already begun to wrap you in its quiet and peaceful embrace, then may your dreams carry you gently through the infinite stars, floating weightlessly through curved space-time, dancing with gravitational waves, exploring the quantum foam at reality's deepest level. Until next time, rest well in the knowledge that you are part of this magnificent cosmic story. Remember always that the universe is here, quietly unfolding its secrets around you. Sweet dreams. And may you wake tomorrow with renewed wonder at the beautiful mystery of existence. Sleep peacefully, knowing that somewhere in the cosmic dark, new stars are being born. Black holes are dancing their final spirals, and gravitational waves continue carrying the universe's ancient songs across the vast ocean of space and time.